Hello, everyone. Welcome to another exciting Wednesday night on York Observatory TeleTube or our YouTube live streaming channel. Tonight we have a great astronomy and astrophysics program lined up for you, written and presented by our students, faculty, alumni, and friends. Tonight we have an amazing lineup of Jean-Luigi, Gagan, Palvisha, Anita, and Michael. So take it away, team.
Thank you, Dr. Hyde. Hello, everyone, and welcome to our Wednesday night live stream presented by the Alan I. Carswell Observatory at York University in Toronto, Ontario. I'm Guggen, and I'm here with Anita, Jean-Luigi, Michael, and Palvisha, and we'll be your hosts for this evening. If you have any questions, please drop them in the chat or the comments section below. Today, we'll be learning about planets. Both our neighbors in the solar system and distant planets around other stars. Let's start with the basics. What is a planet? In the past, planets have been defined in different ways. Currently, the definition that is most widely accepted is the International Astronomical Union's definition of a planet in our solar system. The AU definition states that a planet is an astronomical body that orbits the sun, is massive enough to be rounded out by its own gravitational forces, and has cleared the neighborhood around its orbit. Clearing the neighborhood means that the planet's orbit is relatively free of dust particles from the star's protoplanetary disk, and this process occurs during the early life of the planetary system, which you'll learn more about in a little bit. Other definitions of planets also include the condition that they must not be massive enough to undergo thermonuclear fusion, which is the process by which a star burns and gives off energy. When we see planets such as Mars, Venus, Jupiter, and Saturn in the night sky, they appear very bright. However, the light that we see is the sun's light reflected off the planet's surface. Planets do not produce or emit enough of their own light for us to see them with the naked eye unless they are shined upon by the sun. The solar system is a gravitationally bound planetary system around our sun. It includes 8 planets in order from the sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. All of these planets orbit the sun on a relatively flat orbital plane called the ecliptic, as shown in the diagram on the bottom right. The solar system also includes other bodies, such as satellites, dwarf planets, asteroids, and comets. Satellites are astronomical bodies that orbit other planets, such as our moon and the moons of other planets like Jupiter. Dwarf planets are more similar to planets, but fail to meet some important criteria, and asteroids are much smaller irregular rocky bodies. Comets are small bodies made of dust, rock, and ice. The asteroid belt is a region between Mars and Jupiter's orbits where many asteroids orbit the sun. Beyond the giant planets lies the Kuiper belt, a region that contains asteroids, comets, and dwarf planets. Still further than that, and extending to the far reaches of the solar system, is the Oort cloud, a vast region of space containing icy bodies and where most comets originate from. You'll learn more about the formation of the solar system later on when Palvisha will take you through 2 important theories of its formation. For now, let's focus on the planets. Terrestrial planets are planets that are rocky or solid, similar to the Earth, hence their naming after the Latin word for Earth, terra. In the solar system, the 4 terrestrial planets are the inner planets Mercury, Venus, Earth, and Mars. Each of these planets has a metallic core surrounded by a mantle and a solid rocky surface. They are much closer to the sun than the 4 giant planets and are much smaller than the giant planets, and therefore much more difficult to detect as exoplanets. An atmosphere is a layer of gas surrounding a planet. Terrestrial planets have secondary atmospheres, which are atmospheres created by internal volcanic activity or comet collisions, rather than primary atmospheres, which are created through matter accretion during planet formation. Secondary atmospheres are much thinner than primary atmospheres. Some satellite objects in our solar system have characteristics similar to terrestrial planets, such as some of the larger moons, but they are not considered terrestrial planets due to the fact that they orbit planets rather than orbiting the sun directly. Giant planets are planets that are much more massive than terrestrial planets. In our solar system, the giant planets are the 4 Jovian planets Jupiter, Saturn, Uranus, and Neptune, which are the 4 planets furthest from the sun. They do not necessarily have solid cores, and therefore some have no solid surface. They usually are gaseous, with thick atmospheres composed of helium and hydrogen. All of the 4 Jovian planets are gaseous. The atmospheres of giant planets are primary atmospheres, formed by accretion of matter from the star's protoplanetary disk. These atmospheres are much thicker than those of terrestrial planets and make up most of the planet's mass. Extrasolar giant planets are much easier to detect than small terrestrial planets, and therefore make up more of the known exoplanets. While giant planets are usually gaseous, there are some examples of giant solid exoplanets. Now, some of you may be wondering, what about Pluto, the 9th planet? Well, actually, based on the IAU criteria of a planet, Pluto is not considered one. It is considered a dwarf planet. The IAU defines a dwarf planet as a body orbiting the sun massive enough to be mostly rounded, but has not cleared the neighborhood around its orbit and is not a satellite. Pluto, which is a small body, usually beyond Neptune's orbit, does not have a clear orbital path. It has not cleared its neighborhood and therefore cannot be considered a planet. There are several other dwarf planets in our solar system, with one of them being Ceres in the asteroid belt, and there are many more in the Kuiper belt beyond Pluto's orbit.
Great. So now that we know about the different types of planets in our solar system, the question now is, how are they formed? This leads us into the formation of our solar system. There are a few theories as to how our solar system formed, but I'm going to be covering 2 of them today, starting with a widely accepted theory known as the solar nebula theory. But before we jump into theories, I want to talk about what a theory is and what constitutes as a good theory with respect to our solar system. So, theory is a hypothesis that has significant proof to support it, which means a good theory for the formation of our solar system would have to have significant proof to support it, and also require it to explain many essential aspects of our solar system. To name a few, it would have to explain how the planets were formed, the satellites, so the moons, and why Venus and Mercury don't have any, the arrangement of the planets with the rocky planets closer to the sun and gas giants farther out, the orbits of the planets around the sun and why they orbit in the same direction, the inclination of the orbital plane, the existence of the Oort cloud, and Kuiper belt objects, and much more. So now that we know what constitutes as a good theory, let's dive into the most widely accepted theory of formation, the nebular theory. The theory developed from what was known as the nebular hypothesis, first suggested by Immanuel Kant and Pierre Simon de Laplace in 1796. There is now a significant amount of evidence to support this theory. So it is, or this hypothesis, which is why it's now a theory. The nebular theory proposes that the sun and the planets formed out of the gravitational collapse of a large nebulous cloud. This cloud was made of primarily hydrogen and helium. As the cloud collapsed upon itself, it heated up and matter, or atoms in the cloud, started to collide, causing the cloud to heat up. Eventually, the matter reached a temperature at which hydrogen fusion occurred, and from this, the sun was born. Due to the intense heat from the birth of the sun, the leftover material from the nebula formed an accretion disk around it. This was a rapidly rotating accretion disk. Matter fused together in the accretion disk, first forming planetesimals, and these attracted more matter, forming protoplanets. The protoplanets existed for around 10 to 100 million years, and over time, more collisions occurred and more fusions occurred. So protoplanets got bigger or smaller, or were completely destroyed. And eventually, the 8 planets that we know today were formed. Stellar wind from the sun stripped away most of the gas surrounding the inner planets, leaving them small and rocky, with the gas giants spared as they were farther out, which explains why the rocky planets are closer to the sun and gas giants are farther out. Another reason for this is because collisions were much more frequent and violent closer to the sun, so it was really hard for protoplanets to grow in size. Now let's talk about a second theory, one that's not as widely accepted, and the reasons why it isn't. This theory, or rather hypothesis, as it did not have sufficient evidence to support it, is called the tidal hypothesis. This hypothesis was formulated to explain why all of the planets orbit the sun in the same direction and in nearly the same plane. It was postulated by James Jeans in 1919 and modified by Harold Jeffreys in 1929. This hypothesis, proposed in the early 1900s, suggested that another star happened to pass by the sun. Tidal forces from the star elongated the sun and drew out a long stream of material out of the sun. This matter, drawn in the same direction, would then logically orbit the sun along the same plane and same direction. Makes enough sense. Then why is this a failed hypothesis? Well, In the 1930s, it was determined that a tidal force strong enough to draw out a filament from the sun would also be strong enough to break and disperse that filament, and so no planets would be able to form. The hypothesis also failed to explain the distances of the planets from the sun. Tidal forces would result in the planets being formed closer to the sun than they are now, and another issue was with the angular momentum. Planets formed from tidal forces would not have as much angular momentum as the planets do at the moment. So there was not enough proof for this hypothesis to become a theory like there was for the nebular theory.
All right, it's undoubtful that over the decades, space planetary exploration has been at the focus of attention for astronomers, giving a deeper insight at our neighborhood. The following are just some of the planetary missions, so don't feel upset if your favorite mission was not mentioned, and if you think we should invest a presentation about more planetary mission, please comment below. All right, so early missions and the desire of sending probes out of Earth's atmosphere began about the late 50s when both US and USSR tried to send robots to the moon. After the moon, it was just a matter of time for both countries to focus on other objects. Some of the early significant accomplishments of planetary missions in early stage were the Soviet Venera mission. The Venera exploration took about 2 decades and nearly 15 probes to successfully identify some features of the atmosphere and surface composition of Venus. This mission actually had some firsts in the history of exoplanetary missions. Venera 3, first probe to crash into a planet in 1966. Venera 7, a first probe to land softly successfully on a planet's surface, transmitting for about 23 minutes. Venera 9 and 10, first probes to photograph the surface of another planet, and Venera 15 and 16, first high-resolute orbiter with an imaging radar that managed to map a quarter of the planet Venus, as you can see into the slides. Despite taking so many years of improvements, this mission gave great insight about Venus' composition, on how its rocky non-radioactive surface elements, such as granite and some igneous rocks, were actually similar to Earth. Now, possibly one of the most amazing mission, in my opinion, the Voyager mission. Thanks to a rare geometric arrangement of other planets, the probes easily swing from one to another, bending the spacecraft path along the way while increasing their velocity. This spacecraft was launched in 1977 from NASA, planning to studying the 4 giant planets. Voyager 1 reached Jupiter in March 1979 and discovered and observed for the first time a thin ring circling the planet. As well, it discovered several of its moons, plus 2 new moons like Phoebe and Metis. Once it reached Saturn in November 1979, it immediately discovered 5 new moons and further details on the ring system evolving the planet. The spacecraft also found that Titan's atmosphere was composed of 90% nitrogen. This amazing discovery suggested that this moon, aside Earth, might reside liquid on its surface and periodic chemical reactions. Lastly, the spacecraft took about 60 images of the first portrait of our solar system as seen from the outside. Incredible! Even though Mercury and Mars actually cannot be seen. The images were taken when the spacecraft was about 40 astronomical units away from the sun, about 3.7 billion miles away. As the other spacecraft, Voyager 2 actually was the first one to explore all 4 giant planets. Once it arrived Uranus in 1985, discovered about 10 new moons, 2 new rings in addition to the older ones. And after 4 years, the robe reached Neptune, where took some of the most amazing images of the planet, such as the lesser dark spot, the great dark spot, and the scooter. Probably when it arrived to Neptune, he took some of the most amazing images of its largest moon, Triton, revealing that it's the coldest known planetary body in the solar system and having a nitrogen ice volcano on its surface. In August 2012, Voyager 1 became the first spacecraft to cross into interstellar space, and Voyager 2 in November 2018. Lastly, before we conclude, in my opinion, these are some of the current future exploration that are happening and they already have established a mark in the history of astronomy books. First of all, Juno. If you thought Voyager 1 and 2 did a great job studying Jupiter, the giant of the giants, get ready for Juno. Juno arrived at its destination in 2016, currently analyzing the existence of a solid planetary core, mapping Jupiter's intense magnetic field, and measuring the amount of water and ammonia in the deep atmosphere. This mission serves not only to understand how the giant planets formed, but possibly understand better how the solar system itself formed. Second, Curiosity. This advanced rover landed on Mars in 2012, and it's currently searching the planet for past or current evidence of microbes, which pretty much are small life. To determine the habitability of the planet, the rover on board laboratory will study rocks, soils, and the local geological setting in order to detect chemical building blocks of life, such as forms of carbon, on the actual planet, assessing if the Martian environment actually had life in the past. And lastly, New Horizon. As the name says it, New Horizon is a new journey of space exploration using satellites outside of Neptune's orbit. New Horizon was launched in 2006 and reached our dear planet Pluto in 2015, giving some amazing and spectacular images. Now it is heading towards the Kuiper Belt to examine some of the ancient material of our solar system.
All right, now let's talk about one of the questions that always comes to our mind. Are we alone in the universe? To find the answer to this question, today we'll go beyond our solar system. Planets that orbit a star other than our sun are called exoplanets, and based on their size and composition, we can divide them into four main categories. The smallest ones are terrestrial planets that can be found in Earth's size range. They are mainly composed of heavier elements and they don't have a significant amount of atmosphere. In super Earths, the mass of the planets varies between 1 to 10th of the mass of the Earth, and they are made of rocky or icy material. Another category of exoplanets consists of Neptune-like planets, which are gaseous and have the opportunity to become ocean planets if they migrate to the habitable zone. Some known as gas giants probably have a small rocky core with composition of hydrogen and helium, and they were the first discovered exoplanets. In 1995, the first exoplanet called 51 Pegasi b was discovered as it was orbiting a sun-like star. Since then, more than 4,000 exoplanets have been discovered and thousands of them are waiting for more observations to be confirmed. Now, the challenging question is, what makes an exoplanet habitable among all the discovered ones? To find a habitable planet, both size and composition of a planet and a star are very important. The region around the star where a planet with a sufficient atmosphere pressure can maintain liquid water on its surface is called the habitable zone. Another important factor to have a habitable planet is the lifetime of the home star. At least a few 100 million years is needed for the microbial life to form, so the home star should live long enough to be suitable for both humans and animals. Now the question is, have we ever found a habitable planet like Earth? Well, the answer is yes. Kepler 186f is one of the few Earth-sized planets that is in the habitable zone. Its home star is smaller and cooler than our sun, and it takes 130 days for this planet to orbit around its own star. This planet was discovered by NASA's Kepler mission, and it is about 500 light years away from Earth in the constellation of Cygnus. Another Earth-sized exoplanet in its star's habitable zone is TOI 700d, which has been discovered by NASA's TESS mission. It orbits around a cool M-Dwarf star, which is about 100 light years away in the constellation of Dorado. And finally, let's talk about the closest exoplanet to Earth, which is about 4.25 light years away from us, and it's called Proxima Centauri b. This planet is a super Earth, and it orbits an M-type star in the constellation of Centaurus. Although it is in the habitable zone of its own star, the generated energy due to the radiation strip away essential elements such as oxygen and nitrogen over time. Now that we learned a lot about exoplanets, do you still think that we are alone in the universe?
Great, so now that we know a little bit more about exoplanets, let's discuss some of the techniques used in detecting them. There are a few ways of finding exoplanets, some more effective than others. For the sake of time, I will be discussing the most common methods used in research today. Those are the transit method, radio velocity method, and direct imaging. In astronomy, when one object passes in front of another, it is called a transit. To detect a planet using the transit method, researchers continuously observe and record the brightness of a star on a light curve. When a planet transits the star or moves in front of it, it blocks some of the star's light that we receive, and researchers measure the dip in the star's brightness. The resulting light curve is used to provide information about the planet, information such as the size of the planet, the period of the planet, meaning how long it takes to revolve around the star once, the distance between the star and the planet. This helps us determine if the planet is within the habitable zone of the star. And in some cases, the composition of the planet, meaning what elements may be abundant on the planet. In order for the transit method to be effective, the planet star system must be edge-on to our line of sight, meaning we have to see the planet move in front of the star rather than just around it. While the transit method can detect planets in a wide range in sizes, it is biased to detecting larger planets as they cause a greater dip in the star's light curve. Scientists usually require at least 3 consistent dips in a light curve before concluding that a planet is the cause. And according to NASA, 3,169 planets have been detected using the transit method as of today. A popular misconception is that a planet orbits around a star. However, in reality, both the planet and the star orbit their common center of mass. This is because just as the star has a gravitational pull on the planet also has a gravitational pull on the star. A Doppler shift is a change in frequency of a wave when the observer and the wave source are moving relative to each other. The radial velocity method relies on the orbiting of a star around its center of mass. It measures the shift in the light it emits based on the direction that it is moving. As you can see here, as the star moves away from us, it emits a redder light, or it is red shifted, and as it moves towards us, it emits a bluer light, blue shifted. If we notice a Doppler shift, that means there is a planet that we may not be able to see exerting a gravitational force on the star, causing it to move back and forth. Similar to the transit method, the radial velocity method can detect planets in an edge-on system. The radial velocity method is biased towards finding larger planets that are closer to their star, as these planets would exert a stronger force on the star, causing its movement to be stronger and more defined. The radial velocity method can tell us the mass and period of the planet, and combined with the transit method, we can calculate the density of the planet. And according to NASA, 804 planets have been detected using the radial velocity method. The best way to learn about an extrasolar planet is to look at it directly. Unfortunately, that is quite difficult to do, but it is not impossible. Current technologies can detect exoplanets directly, but only in some cases and with very low resolutions. This method observes the light that is emitted by a planet's atmosphere using infrared wavelengths, as that causes the planets to appear brighter. Even though the planets do appear brighter in the infrared, we still need to cover or reduce as much of the star's light as possible in order to see the orbiting planets. The direct imaging method is biased to detecting larger, hot planets as they emit more light. These planets, however, usually do not have suitable conditions to host life and are not really considered in the search for extraterrestrial life. Here is a 4-planet system in orbit directly imaged. The black circle in the center helps block out the blinding light of the star, making the planets more visible. And according to NASA, 49 planets have been directly imaged so far. Although many exoplanets have been detected, finding Earth-like planets has been very rare. However, on July 23, 2015, NASA confirmed the first near-Earth-sized planet called Kepler 452b within the habitable zone of a sun-like star. The Kepler Space Telescope, a telescope launched by NASA in 2009 to detect Earth-like planets, detected the planet using the transit method. Located 1,400 light-years away in the constellation Cygnus, Kepler 452b is 60% larger in diameter than Earth and is considered to be a super-Earth-sized planet. On the top right is an image showing the size and scale of Kepler 452 system compared alongside the Kepler 186 system and to our own solar system. Scientists believe that Kepler 452b has been in its star's habitable zone for about 6 billion years. That's longer than the Earth has even existed. So think about it. If the planet does have a similar composition as Earth, many forms of life may have been able to evolve on it with this amount of time. On the bottom right is an artist's representation of what a planet like Kepler 452b might look like, but since we cannot directly image it, we have no way of knowing that that is what it actually looks like. Exoplanet research is a relatively new field and continues to grow more and more each year with fascinating new discoveries. As of today, Kepler 452b is one of the few planets that we know of that has the potential of being habitable and being the home to life like us. Well, everyone, you've been listening to the Alan I. Carswell Observatory's weekly TeleTube broadcast, the Astronomy and Astrophysics program, written and presented by the students, faculty, alumni, and friends of York University. The hosts this evening have been Anita, John Luigi, Gagan, Palvisha, and myself, Michael. Make sure to leave any comments in the comment section of the video. You can always connect with us on Twitter with the handle @YorkObservatory, and check out our website for show notes, content, updates, and contact information at observatory.info.yorku.ca. Thanks for tuning in, clear skies, and have a good night.
Thank you, everyone. That will be the end of the official broadcast for tonight. Just as a reminder, we will be on chat on our live stream until about 8:30. So feel free to ask us questions in the chat or comments for the next few minutes.